Hi everyone, my name is Jasha Whiteman and I am the co-chair of the AIAA Sydney section with Nimish, who is the host tonight. And today's talk is presented by Doug Griffin, very kindly presented by Doug Griffin, who is a chief engineer at Skykraft, who are designing and developing microsatellite constellations for space-based air traffic services. Doug completed his PhD in hypersonics at University of Queensland, then immediately left for Europe and worked on ESA space programs for a while. In 2015, he returned back to Australia and worked at UNSW Space Program until quite recently when he moved full-time to Skykraft. Doug, the podium is all yours.
Excellent. Thanks, Tash. Thanks for that introduction. So, pleasure to give the talk this evening, and I'm not really familiar with the format, so I've tried to cater for everyone in the audience, or everyone who is potentially in the audience. So, if you're the type of AIAA member or person who's dialed in that is interested in the high-end space in big space programs, I've got some more stories to present about some of the programs that I've worked on in Europe. If you're the type of person who's interested in industry trends, in what is happening in space in Australia and more globally, then I'll have a few thoughts about that. And I know some of you have also dialed in to find out about Skykraft, and what we're trying to do in Skykraft is to link in those big trends and deliver value and create value in space information systems here in Canberra. So I'll leave plenty of time at the end for questions. So I really much appreciate that if you've got any questions or the end. So I'll go through my talk this evening, going through pretty much a chronological history of the different places that I've worked. And I started off University of Queensland doing undergraduate in mech engine, then hypersonics, and then I moved to Italy for a couple of years, worked at Alenia Aerospazio in another lab, a couple of years at University of Oxford, and then I can proudly say that on the 1st of January 2001, which I consider the start of the century, I started working at RAL Space, and I've been continuously working all of this century in space programs and space projects. So what we're about to see now is a big bang, and that big bang is the T4 wind tunnel. It's the wind tunnel that I used when I was doing my PhD at University of Queensland, and that capability was invented, that wind tunnel was invented by my PhD supervisor, Ray Stalker. Ray's big passion was in scramjets, and the promise of scramjets has been for probably 50 odd years of affordable access to space. And the idea there is that you have a supersonic combustion ramjet, and you carry fuel. You don't have to carry your oxidant, and you burn oxygen from the atmosphere, and you get into space with a reusable rocket and do it quickly and cheaply. And that's a really tantalizing prospect. And it was one of the things that really motivated the other PhD students and postdocs and lecturers at UQ is how can we get into space in an affordable manner so that we can make the most of it. After I finished my PhD, I did what a lot of people did. A lot of my friends and cohort did is go and work overseas. So I worked for a little while at an Italian research lab doing stuff in nuclear fusion research, and then I worked at Alenia Aerospazio, which is now Thales, in their advanced projects group, doing what has now become HAPS programs. Then a couple of years at University of Oxford working on projects with Rolls-Royce on cooling of jet engines. And then I made my big move into space. So I started, as I said, at RAL Space in January 2001. So RAL Space and the STFC, I'm probably, I would expect that not everyone in the audience would know about them. So STFC, we can think of as the UK's version of the CSIRO. And the Rutherford Appleton Laboratory is a lab in on an old RAF airfield in Oxfordshire, and it is a bit like Marsfield or Black Mountain. It's a precinct with a lot of science and technology going on. And at the Rutherford lab, there's a department, RAL Space, that I was involved in, that has benefited a lot from the fact that the UK is a member of the European Space Agency. So UK puts in money into ESA, and that means that ESA will invest in programs that are run out of the UK. And RAL Space is the largest space science laboratory in Europe. And when I left, it had been involved in over 200 missions. And it was a really great place to work. And my two war stories from the big end of space has come from my time at working there. So I'll start off with the a mission that I worked on was all about cold stuff. So this is a bit of astrophysics 101. And up in the left here, we've got the Planck curve, and the Planck curve shows what the wavelength of light is that's emitted from a body. So on the left-hand axis, we've got spectral radiance. So that's the amount of energy, amount of power, optical power that's being emitted by something. And on the horizontal axis, we've got the wavelength. So right down the left, we've got the ultraviolet, and then way off to the right, we've got the infrared. And what we can see is that as things get progressively cooler, the amount of energy that they emit goes down, but also the wavelength goes longer and longer. It becomes more and more infrared. And astrophysicists and space scientists exploit this to carry out their work. So this view on the right is a view of the Coalsack Nebula, which is familiar to us in the Southern Hemisphere. It's right next to the Southern Cross. And what we see in these dark areas is not the absence of stars, but it's actually the presence of cold clouds of dust and gas. And why is dust and gas interesting, you may ask? Well, the reason is that these are the areas where stars are formed. So the formation of stars is actually really poorly understood. What needs to happen is that the cloud of hydrogen and other elements needs to be compressed and get high enough density so that nuclear reaction can start. But just as if you've got a bike pump and you block off the end, you push down, it gets compressed, gets hot, and bounces back. And that's kind of the tug of war that's happening in space, and it stops stars from forming. But there's something goes on that allows the clouds to condense and get to high density so they can ignite without getting hot. And that's what this mission is all about. So in 2009, the European Space Agency launched the Herschel Space Observatory, and it looks at very cold things. And the spacecraft is pretty impressive. The telescope itself is the biggest single telescope that's ever been launched into space. It's a 3.5 meter diameter silicon carbide mirror. And when it's in space, it cooled down to very cold, cryogenic temperatures. There's a tank of cryogenic superfluid liquid helium in this black vessel on the right, and the telescope got down to 85 Kelvin. And that allowed all the optics in the cameras not to be dazzled by the light that comes off the telescope and the optics, and to see into these very dark areas. So this is the suite of instruments that was on the spacecraft. So I was a systems engineer on SPY, this one on the top left-hand corner, And then there was another instrument called PAX, which was an imager and a spectrometer. And then there's the hi-fi instrument, which is a very high resolution spectrometer. This is a view of the spacecraft in the large acoustic facility in Noordwijk in the Netherlands. And I supported this test, and this the spacecraft gets locked up in here, and they close the doors, and they have absolutely huge acoustic sources coming out of these holes on the left, and it gets vibrated with that acoustic energy to make sure that it will survive launch. And then down on the right is a view of the spacecraft being prepped with some optical test before delivery to Kourou. These are some of the subsystems on that Spire instrument that I was a systems engineer on. So on the left here, this is a Californian detector module. It was cooled down to 0.3 of a Kelvin above absolute zero, so 300 millikelvin. This is a French cooler that cooled it down. That was designed and built in Grenoble. This is a Scottish mechanism, this beam steering mechanism to steer the image across the detectors. This is a French scanning mechanism from Marseille, and this is a slightly younger version of me and Alan putting it all together. So in Oxfordshire at RAL, where we did the calibration and all the testing and a lot of the operations from. So what were some of the scientific results from Herschel and from Spire? Well, this is an image of a galaxy. It's the Andromeda galaxy. It's in the whole scheme of things, it's pretty close. And we've also got this M110, the Messier object M110 off to the left. This is an elliptic galaxy, and this is a spiral galaxy. Elliptical galaxies are old and don't have many areas where stars are formed, whereas this spiral galaxy is actually very rich. It's relatively young and rich in star-forming regions. So this is what you see if you look through, if you have a Hubble-like image or a good telescope on the ground over a long period of time. But this is the same view from Herschel, and you can see these red areas, these lanes, these spirals are where the gas and the dust is cooling down and emitting and condensing, and these are the areas where stars are formed. And I just love flicking between these two images, seeing the difference between what you see visibly and what you see in the far infrared or sub-millimeter wavelengths. So we've also got an opportunity, or we had an opportunity with Herschel to see these star-forming regions right up close. So we don't have to look at the next galaxy. We can use our own galaxy and look at the Milky Way and look at areas where there's star-forming regions in our own galaxy. And what we saw with the Herschel and with the PAX and the Spire instruments are these lanes, these filaments in these clouds of dust and gas. And when you zoom in close, you can see that these filaments are where the stars can actually ignite and condense and ignite. So it's pretty exciting science. So we moved from the very cold, the Herschel mission, onto something very hot. And this is another big mission I worked on. I managed one of the instruments on this. And this is looking at the sun. And the sun is our closest star, obviously, and it's a really great place to understand heliophysics. And there are things about the sun which really are very, very much poorly understood. We know that at the core of the sun, it's very hot, and that's where all the nuclear reactions go on, and that's where all of the heat's generated. And then as the heat conducts out or is transferred out from where it's from the middle, right in the core, it gets progressively colder. So it starts off in the middle at 15 million Kelvin and then goes out to 10 million, then 600,000, then right on the surface, on the photosphere, what we see on a good day here in Canberra is that the photosphere is at 6,000 Kelvin. But the really bizarre thing is that as you go out further though, it heats up. You'd expect as you go further and further away, it cools down. Well, no, it doesn't happen on the sun. It actually gets hotter in the atmosphere. And I can genuinely say scientists don't know why that happens. They also don't know why there's variability. They don't know why there's a solar wind, and they don't know why what happens on the poles of the sun. Nobody's been to the pole of the sun, north or the south pole of the sun, and so ESA and NASA teamed up and did the solar orbiter spacecraft, and this spacecraft was launched earlier in the year, and it carries a suite of instruments to study some of these phenomena. And it flies very close to the sun. It goes to nearly 4 times closer to the sun than what the Earth is, which means that it's about 16 times hotter than the sun is 16 times hotter because it's an inverse square law. And that means that the spacecraft gets very hot and the instruments get very hot. And we need to have this heat shield on the front, which gets, when it gets closest to the sun, it gets very hot. It gets so hot that it's actually glowing red hot at the front surface, or at least cherry red at the front. And then inside, protected by that sun shield, is all the suite of the instruments. And those instruments are broken up into 2 sets. There's the remote sensing cameras and spectrometers that look down and look in the different wavelengths of the light from the sun. And there's also some in situ instruments that actually measure the atmosphere and the radio waves and the magnetic field actually flying through the atmosphere of the sun. It's that close, and it links those 2 up to gain an understanding of those questions that I spoke about earlier. So this is the instrument that I managed when I was at RAL before I left. It had a Swiss door, a British mechanism, a German mirror, American detector from Washington, another Swiss mechanism, and a French grating, and an American electronics box. These programs are very international in flavour. So, as I said, it was launched earlier in the year. It was launched just after COVID broke out, and it was launched successfully. And they turned on all of the instruments, and all the instruments have come to light. And it's pretty exciting, actually. So, this is a image. I'll just play it now. Of some of the results from one of the images, the EUV imager. And you can see on here, just where the cursor is, there's these little white flares, these little white dots that are appearing. And these white dots haven't been seen before, and they're called nanoflares, and they're million or even up to 1 billion times smaller than the flares that are seen during solar storms. And what the solar physicists are calling these things are campfires. And it's speculated that this could be part of the reason why the atmosphere of the sun is hotter than the surface of it. On the right is this a spectrogram from the SPICE instrument, the one that I worked on, and that's picking up the composition of the atmosphere, and it'll also be able to measure the Doppler shift of the gas. So if it's being ejected from the surface of the sun, it'll be going towards the spacecraft, getting blue shifted, and we can actually measure the velocity of the gas and get an understanding. So that is the I guess the techie part of the talk. So what are some of the reflections of having worked for 15 years in that context? Well, the reputational, financial, opportunity costs for getting involved in these big programs are very significant. If something like Solar Orbiter doesn't work, it's going to be very difficult for ESA, and it's very costly. It's order of $1 billion, and you're spending that $1 billion on Solar Orbiter, not on something else. So the stakes are high, and they're pretty much too big to fail, these programs. At the same time, if you're going to be spending that amount of money, you need to be ambitious, because there's really stiff competition between different missions to get selected. So you need to be doing top quality science, and that makes the engineering more challenging and the technology more challenging. Fortunately, we do have systems engineering, and ESA is very good at systems engineering. And by using good discipline there, these programs, even though they're built up of huge agglomeration of consortia and industrial procurement programs, they do work. And you actually get inspirational outcomes, provided you've got a lot of patience, a lot of dedication, and a lot of money to get them going. So in 2015, I finished up at RAL and moved back to Australia and had a complete context change. So I moved from what are called big space into what's variously called as new space. So new space is moving away from those big programs that take several decades to implement, into a more agile approach. And I worked at from 2015 until earlier this year in March at UNSW Canberra Space and helped set up the engineering effort there. The program there is going to be remembered when the history is written for the space program in Australia during these years as being a real catalyst of building the space economy in Australia. So the first mission that was launched by UNSW was a partnership with DST Group on the Buccaneer program. Then came the M1 mission, which wasn't a huge success, but it was very successful. The M2 Pathfinder mission, which was launched earlier in the year. And the team over at ADFA are now preparing for the M2 mission, which is going to be a very inspirational mission. So Skykraft, I moved here in March this year, and full-time now, focusing 110% on getting the company on its feet. And at Skykraft, we see that constellations of small satellites are the way of the future. And on the right here, I've just got a small simulation of a constellation of spacecraft flying around over Australia. So why are constellations important? Well, ultimately, if you're launching a spacecraft, you're actually delivering a service. And a service is something which is actually providing a benefit to somebody on Earth. And if you're delivering a service, well, it's best if you don't just deliver it to one area, you deliver it globally. And you can see from on the right that with enough spacecraft, you can actually fly a constellation and deliver services globally. And if you're delivering services, you want them delivered in a timely manner and ideally in real time. And that's what you can do with a constellation. And if you're dealing with data, then you want to add as much value to that data as possible. And then if you're adding value, then you want to make sure that whatever you're flying in space is interoperable with what's on the ground. A lot of times, the systems that we're talking about in space are actually less expensive than the systems on the ground. So our mentality, our mindset is to look at how to adapt what's in space to the system on the ground. And then ultimately, if you're doing all of that, you need to really have a mind on the economics and the business case, and making sure that you're not just setting up your mindset and your approach to developing one exquisite bespoke spacecraft, but a series of spacecraft which are affordable and quick enough to design, build and test. So that's what we're about. And what markets are we looking at? So low Earth orbit communications is a prime target. Delivery of Internet of Things services, intelligence, surveillance and reconnaissance, space situational awareness, data analytics, geospatial intelligence. And the one that I'd like to spend some time on is air traffic management. And the reason I'd like to talk about air traffic management is that it really aligns well with this business and technology strategy that I've spoke about on the left. But it's a new thing. It's an area where there is customer demand, a customer pull, and it's an area where we've got capability at Skykraft to really make a a product which is global impact and global significance. So what are we doing? We're developing a constellation of spacecraft that are going to deliver a comprehensive suite of communication, navigation, and surveillance services for air traffic management. So that's everything from picking up the navigation beacons, the ADS-B beacons, to some of the voice and the data communication services that are transmitted on the VHF. And what we're implementing at the moment is a program of 4 launches, and we're developing that in a spiral approach. So the first spacecraft that we'll be launching next year is going to be very simple, a very simple spacecraft, and it's got one objective, and that is to provide some test data for the viability of using aviation band VHF from space. That's something that the ITU and the World Radio Congress are investigating, and Skykraft needs that to happen. So we're doing that. And that'll be followed up with more launches of our spacecraft design that are going to have increasing fidelity and to the final design. So some of the technology we're working on to make it a global service that delivers real-time data, we need to have a system to be able to network the spacecraft, and we're developing RF communication systems and antenna pointing mechanisms to interconnect those spacecraft either to each other, but also provide those downlinks as well. We also have got we're very pleased and fortunate to have received been successful in a grant application to the Australian Space Agency in their International Space Initiative. And the the Australian Space Agency International Space Investment Initiative helps unlock space opportunities for Australia. It expands capability and capacity for the Australian space sector. There's been 10 projects funded under the program with $11 million in grants, and it's supporting 24 businesses and research organisations in Australia, and to build bridges with 10 international space agencies, companies, and research organisations. So what's our program? So we partnered up with a local company, a leader in carbon fibre manufacture, that's X-Tech, and they have a proprietary technology, the hydroclave technology, which enables them to build high integrity carbon fibre structures. We've got the carbon fibre structure illustrated here with a complement of 30 spacecraft on board, and that structure integrates onto the top of the launcher and then deploys the spacecraft when they're on orbit. And we're looking to build a proto-flight version of that and test it and qualify it mechanically next year. The big advantage of that is it's an economical way to deliver the spacecraft into orbit. It doesn't make much sense to make the spacecraft without some sort of a plan of getting them up there. And this carrier, this launch stack and hold down mechanism is the pathway for us. So what are some of the reflections of working in this under this new paradigm, this new way of thinking under this new space? Well, reassuringly and comfortingly, the rules of physics and engineering science and astute engineering management remain intact. It's a new spacecraft is just a spacecraft, and all these things remain true. What is different though is a lot of the activity is really driven by SMEs like Skykraft, and is really commercially focused. And the other thing that is different is that the spiral or agile or DevOps approach to engineering development are really feasible in this sort of environment. It would be unthinkable to build a Herschel or a solar orbiter and just that's $1 billion program and launch a prototype of it to test one piece of technology. That just doesn't work. But what we can do with the much more affordable access to space that we have these days is to incrementally build capability. And so we've got the ability to test our VHF payload on our first launch and then build on that, and with that DevOps approach. And there's lots of benefits from doing that. And then given we're seeing two things at the moment. We're seeing the small sat revolution of new abilities to develop and deliver services with compact microelectronics from small spacecraft. But we're also seeing the cost of launch going down, and these two coming together at the same point in time in history is going to produce some unexpected outcomes. So that's about it for me for my presentation. So thanks very much for listening, and I'll hand it back to you, Tash. I should have given you a warning. Yep,
Apologies, Douglas. I couldn't unmute myself. Nimish had to unmute me. So I've got a few questions. So a few people submitted questions. So we have questions from Steve, who's asking, what is the right size for Australia's space industry? Do we have any competitive advantages?
So the right size for Australian space industry, the way I would look at that is that there's an element which, particularly for defence, where there's big advantages to have sovereign capability. But I think that there's real advantages in not being too parochial about your space capability. And remember, particularly in the civilian domains, is that we're looking at delivering services globally. So it's not so much what's the right size for Australia, but what markets can we address globally. And so that sort of scales. If you're delivering global services, then you can look to get revenue from multiple countries, but also be a bit bigger. What competitive advantages do we have? I think it's probably an advantage and a disadvantage. So I guess disadvantage, we're not ensconced in a mature space agency. So the Australian Space Agency is very, very new, and it's still building up capability. And I guess it'd be fair to say it's finding its feet in the world. If you look elsewhere, you've got JAXA, NASA, the Canadian Space Agency, UK Space Agency, ESA. All of the other places around the world have a lot more heritage in space missions. So there's a lot more people that have got space training, but then it's also working very much under the big space paradigm, which has its place, absolutely. There's some things that you need to have big capability to do, but I guess there is a real opportunity for us to invent and cement our place in the world with small satellite technology.
All right, thank you. Michael is asking, how easy or difficult was it for Skykraft to navigate its way through the requirements of the Australian Space Act to achieve an Australian launch authorization? Does it get any easier for each follow-on space missions?
Yeah, the first time you do it. So my experience has been with particularly with UNSW under the old Act. It was a little bit more complicated, and it's very much been streamlined for those wanting to launch spacecraft. So I'm quite positive about the prospects there. I think it's an enlightened view of removing friction.
Very good, thank you. Now, Jackie, if the Australian Space Agency had not formed, would you have stayed in Europe? How hard was it to return to Australia and join back to the space ecosystem?
Sorry, could you repeat the question?
If the Australian Space Agency had not formed, would you have stayed in Europe? How hard was it to return to Australia and join back into the space ecosystem?
Yeah, it was. So that's a very personal question. The work that I did in the UK in the ESA system, I loved it. It was a passion. It's a friend of mine who's sadly no longer with us described it a bit like a drug that you can't stop when you get hooked on doing space missions. You can't stop. And working on the big science missions is very inspirational. So I'm an engineer. I don't claim to have any novel insights into space science or astrophysics, but working with those scientists and physicists and enabling them to develop that experiment is a lot of fun, and it's very inspiring. So coming back to Australia wasn't a lay down misere, but what I could see is that there was going to be big opportunities to shape what happens in Australia, and that's also professionally quite a positive prospect. That you can move into Australia 5 years ago was really crawling, and now I'd like to think that I played a part in helping us stop crawling, and we're toddling along now.
All right, thanks. So we've got a couple more questions. One's from Julian. Are there any differences in approach to systems engineering between Europe and USA, Japan, UK, India, the rest?
So between my main experience has been with the European Space Agency, more or less the ESA standards, the ECSS standards are accepted by NASA and vice versa. So the Solar Orbiter Helio HI instrument, the heliospheric imager instrument, was built by the NRL, which is the Navy Research Laboratory, US under NASA rules, and ESA would have just accepted them as being compliant to or equivalent to their standards. Similarly with JAXA, I have worked with them. It's probably a little bit of culturally inspired differences working with JAXA. Started to work with India now. I see that their programs are very much, I'd say, streamlined. So a light touch approach to it. I'm not sure whether that's completely fair, but I think that probably the systems engineering documentation, from what I can see, is probably less formalised in India.
So actually, this is my question, is have their lessons, so obviously you mentioned that all this cooperation under the rules of NASA and then that ESA accepts, were those lessons learned from the Mars orbiter debacle, where they forgot to change the units?
Yeah, it's funny. I was interviewing somebody today, and the discussion was around systems engineering, and I said configuration control is really important, and yeah, it's very much true. Yeah, I honestly don't know how that got through the system. The system does break at times.
Right, and then the question from Nathan is, would you still recommend spending some time gaining space engineering experience overseas, or would you say that the space environment in Australia is at a current crossroads, which presents opportunities not available elsewhere? Doug, the guys are requesting if you can turn off the slides and present yourself during the Q&A.
Yep, sure. Here we go. Yep.
Perfect. Thank you.
Yeah, I guess that's very much a personal choice, I guess. The opportunities to work in big missions. If you want to do that, then you pretty much need to go overseas. There is very little in there's no one building any spacecraft, to my knowledge, that are bigger than tens of kilos here in Australia. So if you want to work on a mission that's bigger than that, then you do need to go overseas. But if you look at what we're doing with our air traffic management program, we're launching 210 spacecraft. Each launch, that's 7 launches with 500 kilos worth of spacecraft. So if you're just going on mass alone, then there's big opportunities here in Australia. I guess and it sort of leads on from why I was convinced to move away from the ESA environment and come back to Australia. It was because you have the opportunity to shape things in a big way. In a lot of ways, when you're entering space engineering, space science in Europe, you'll enter as a cog, and you'll be doing pretty much, I guess, low-level stuff. And you'll work. If you're good at it and dedicated and have the right opportunities, then you can work up and provide direction and management level and high-level input into the programs. Whereas here, you've got the opportunity to steer things from an earlier stage in your career.
All right, thanks. A few more questions. Are you happy to take a couple more questions?
I love it. No, go for it.
All right, Michael is asking, what are some technical risks and scheduling challenges for securing a share ride from a spacelift service?
Yeah, well, rideshare. So rideshare is a. It looks like it's a fantastic opportunity, and it is. It depends on who you're going with. So if you're going on, ultimately the primary payload, the main spacecraft that's being launched dictates the schedule. And if it's held up for whatever reason, then you don't go. And for a company, that can be really painful when you really need to have your spacecraft in the air, generating capability and revenue. If you've got to put up with that delay, that's really quite painful. That's why we're really looking forward to buying our own launches for deploying this air traffic management constellation, because then we're, I guess, to a greater degree, masters of our own destiny.
Right. Thanks. Steve's asking, what are your thoughts on Australia developing a launch industry, not just the satellite, but the launch industry itself?
It would be a great thing for us to have that capability. Geographically, we've got a lot of advantages for launching here, and Australia sovereign defence, or our defence capability, would be enhanced if, in times of needs, we knew that we could access space in a safe and reliable manner. Ultimately, though, you have to spend dollars to do that, and the business case for any activity needs to close. So it's really looking at ways in which we can acquire a launch capability which is compelling from a capability point of view and a price point of view. Technically, yeah, no problems.
Right, thanks. And Sudeep is wondering, as Australia becomes more and more active in space, how do you decide what applications you want to be involved in? Is there a general philosophy for where the space agency here wants to move on? It's a bit of a crystal ball question.
Yeah, it's something which is diabolically difficult to do, because you can look at it almost from a like a command economy point of view, and where you've got technocrats or people that sort of try and gaze into balls or convene committees, science committees or industry committees to decide what makes sense. That works. That's how ESA program works, and that's how NASA's space science program works. It's just a really difficult question to know what's the best way to do it. From I guess as a speaking as a industry representative, I'd like to see that industry has a voice, and the things like, well, I see the launch stack, the thing that the space agency is funding for us. It's a strategic capability, and it gives us a real leg up to build capability in Australia. So they made a good call there.
All right, thanks. Do you have any more questions? We can take one or two more questions if needed while people are typing. What do you recommend? I was going to ask, so we do have younger students here, and what pathway would you recommend for them? Would you recommend that they do the same way that they go overseas to UK, to ESA and come back, or that the Australian space is developing enough that they can stay here and work here without having to build that experience?
Yeah, so I've got a slightly different form of this presentation, and after the slide that I had with the shock tunnel firing and the scramjet flying off into the blue yonder, you know, a picture of my PhD supervisor, Ray Stalker, and Ray said to me when I was graduating from my PhD that pretty much if I wanted to stay in high technology, I was effectively committing myself to self-imposed exile. And that's where, for me, that was going overseas was really the only option to pursue a career in high technology, particularly in aerospace, in that particular field. That's no longer true. I've come back and I'm doing really exciting stuff now, and that wasn't wasn't true 10 years ago. It was starting to be true in 5 years ago, and things are only accelerating. So, yeah, it wasn't really an option for me. Now there are real opportunities for young engineers and scientists and software programmers to get involved in programs and stay.
That's good news. Just to point out, Michael Spanner just pointed out that Dr. Ray Stalker was the first Australian fellow at IAA. So a bit of trivia there. We got a few more questions coming through. Was it difficult to get started working in Europe, as in companies, visa requirements, security clearances, all of that?
So it's where it depends on the individual country. So in the UK, my original visa was sponsored by the Oxford University because I was working there. No security clearance was required. And then when I was working at the Rutherford lab, I needed a new visa. So I had to compete against other European applicants to the job, and miraculously, no one else. I was the best candidate, and I was able to get a visa. But yeah, if you've got a passport, it's much easier. And I would say that places like Astrium Airbus, it would be no, that's not completely true, but it's very difficult to get a job in a company that works in defence in Europe. I don't know, maybe I might be wrong there, but I would suspect it's going to be much more difficult.
Possibly. All right, last question. Julian, again, do you see Australia playing a significant role in lunar exploration and ISRU, given Australian capability in geology, geophysics, and mining?
Yeah, it's not something that I've got a lot of visibility on. probably 10 years ago, I would have had an unequivocal no. But places like Rocket Labs are looking to do a lunar mission, and so what was unthinkable in the past is now becoming feasible, and it was only in the domains of big space agencies like NASA or the Chinese or the Russians that were going to be able to do stuff like that. But now it's with this revolution in launches and the cost of launch coming down, it's no longer beyond our grasp.
Okay, thank you. I think we can wrap up. I think that was it with the questions. Thank you so very much for doing this talk. I'm sure everybody else enjoyed it as well. Big eye opener on some things. And thank you everybody for joining us. Our next talk is on August 25th. So do join us for that. And again, thanks. Yeah, go ahead.
Coming on the 18th.
Okay, sorry, apologies. I was skipping a date. Next talk is on the 18th. Watch for the emails and Facebook posts. Again, thank you, Doug, for your talk. Yep. And
pleasure.
Do you just mind staying on as the room empties? Just thank you.
Yep. Thanks, everyone. Hope you enjoyed it.
Yeah.